All right, welcome everybody, and we are now up to chapter 13, and let's go ahead and get started here.
So we use registers in our systems because we need to be able to store groups of bits. Okay? We talked about how a flip-flop is just a storage device. It's a bit storage device where we can remember the state of an output. And so if you have multiples of those together next to each other, then you can have what's called a register, and then we can store more than one bit, right? But to make sure that they all stay together, we can come up with what's called, as long as they all, to keep them all together and to move them all, all the bits in an orderly fashion, we can come up with what's called a shift register, okay? So it says, let me get down to shift register basis here. So this is just a 4-bit shift register, and it's got what's called a parallel load in. So you see that this is connected to where the asynchronous set would be, and we put a 1 0 0 0 on there. So that's going to load the first one with a 1, and the rest of them it's going to load with a 0. Okay? So that's the first step if we're going to parallel load in a starting value, okay? Or load a 1 into the system that we can then shift out. It says receives 4 bits of parallel data and shifts to the right. So it loads in the data from the asynchronous set on top of the D flip-flop, and then the clock period takes over, or the clock takes over the rest of the time, and these are positive edge triggered. So on the rising edge of this clock, it's gonna push everything through. Remember, in one of these systems, Q follows D. So whatever, that's why we're putting the Q into the next D. We're shifting those bits through the system out to some other digital system. Okay, it doesn't just go out here to these boxes and just stays here. It's being shifted out to some other digital system. Okay, so the shift register is what allows the ease of movement of those bits from one place to another. Okay, and again, this is called a parallel to serial conversion because we load it in parallel and then we shift it right as a bit stream to wherever it's going to go. And here's all the different combinations that you could possibly have. You could have a parallel in, parallel out, where it just kind of passes everything through. You could have a serial in, shift left, right? So it comes in on this side and shifts off to this direction. You could have I always have to be very careful about talking about this chapter because I have to be very specific with enunciating all the parts of SHIFT. Serial in, shift right. Okay, so this is how the data is being shipped in, and then once you get 4 in here, it can then parallel load out. Right? There's also parallel in. This right here is essentially what a ring counter is doing because you essentially move the 1. Or it could be more than 1 bit. But in a ring counter, you only have one of the bits high at once, and then it shifts around, and it rings around back to the front. So you get a constant, it's almost like a constant signal there. You have a parallel in, shift out, serial in right, serial out right. So there's all these different combinations of how you can use a register to move data around, all right? So here, this generic picture of a computer A, computer B, and then we have the shift register that makes the connection between the two, right? So within the computer itself, it can parallel load a lot more data because it's traveling a short distance, right? We're talking about maybe 12 inches at most, depending on the ribbon cable connection. But then if you wanted to send it over a long distance, it's going to cost a lot of money if you try to parallel. If you had parallel cables that could send all this data. So then you take the parallel data lines and then you shift it out through a serial communication string. And then the other side can then accept that serial line of communication in, and it can load the registers internal here, the flip-flops internally here, and then once it has all of the bits, let's see, 1, 2, 3, 4, 5, 6, 7, 8, all 8 bits at once, then it can then parallel load that into the computer. And so that's how the data can transfer from one place to another, right? So that's the general idea of what a shift register is and why we would use them. Now we can talk more about the individual aspects of them. A lot of these, like the parallel to serial load, these examples are just using these JK flip-flops, just generic, I shouldn't say generic, but just standard 74LS 76 JK flip-flops, which is an industry standard, right? So you can certainly build them with flip-flops, and then just like I said, use them as if you were, going to use them like a D flip-flop. So in other words, there is no toggle condition, right? So you see the first one here, this is put into a reset, all right? And then each JK after that just accepts the Q and the Q naught. So it's essentially gonna pass that stuff through, all right? But initially, this thing is going to start putting zeros in to this Q right here, all right? And this one's going to be a 1. And so this is going to override it. So whenever this thing loads in, okay, it's then going to shift all of that data out to this serial output, okay? So the other option, if you're not going to use flip-flops, is to use an IC chip, right? Like I always say, like Steve Jobs always said, when there's an app for that, I always say that there's an IC for that, right? Because, why would you want to do all this wiring when you could just have something else internally wired that way, and then you just have to make the pin connections on the inputs and outputs. So here you go, parallel to serial conversion. Notice the initial load of 0, 1, 1, 1, right? And because it's 0, 1, 1, 1, and because that's an active low input, all right, you see how Q responds. It's 1, 0, 0, 0, okay? And then you can see how D is going to change, right? Because in this case, we're talking about the 4-bit parallel in serial shift out. And that was this one back here, right? The 4-bit parallel load in, shift out with the D flip-flops. And so here you have your Ds and you have your Qs, okay? Lost where I was at. Here we go. All right, so here's serial to parallel. It's kind of going the other way. So you have the serial input load in, and then once it makes its way to the first data bit makes its way to the 4th flip-flop, then you can load that data out, okay? And here you have the strobe here with a clock input, and so this is the result. This is going to be the clock pulse of this one right here, okay? So you've got a clock with some kind of a strobe where you can, maybe it strobes every 4 clock cycles or something. I don't know. But anyway, you have the ability to turn this AND gate on and off and turn the system on and off with the strobe. And let's see. Let's move all the way down to the specific types. And one of them is the ring shift counter. Another one is called the Johnson shift counter. And these are really, if I was asking you to write a crib sheet, I would have you write an example of each one of these on your crib sheet because you'd have to create it for the exam. And I still may ask you to do that for this second exam. So the point behind these is that it says used to create sequential control. We talked about that last time, right? We have a sequence of operations. This is sequential logic. It's used to create sequential control waveforms for digital systems. It's similar to synchronous counters, but do not produce a true binary output. Okay? What they do provide, though, is a sequence of predictable, repetitive digital outputs. Okay? And these are called digital sequencers. If you take PLCs with me, we'll talk about real sequencers used in ladder logic all the time. But these can accomplish the same thing. You can do a lot of what you can do with a PLC with microcontrollers and just digital chips, okay? And so these are called digital sequencer, and this is what a ring shift counter looks like. So it's got that same 4-bit structure here, okay? Notice that in this case, it's the same structure where the Q feeds into the J here, except for the very first one and the very last one. And all you do is ring. I use that. I don't know if that's the official term, but I always say you ring this last one around to the J, right? The very first J. And so you see here on initial power up, using our automatic power up reset, right? Only this time we're going to reset these 3 JK flip-flops, but notice what happens on the first one. This reset is tied high, so it's unused. What we do is we initially set this very first flip-flop. So the Q here, the Q output's going to be 1, 0, 0, 0. Now after the power up here, then this no longer applies, right? This is only up at power up. Initially it's going to put a 1 in here and a 0 and a 0 and a 0. Okay, now that Q, that 0 here, is going to come around to the front. And now you're going to have, in this case you'll have a 0, 1. You'll actually be in a reset condition, and that'll produce a 0 here. Okay, so what it'll do is it'll push that 1 through to here. Now this output will be 1. That'll get clocked in the next clock cycle, and this one will become 1. And then after the next clock, in this case it would be the fall, right? So the falling clock edge would then push it to the next flip-flop, and then that flip-flop 1, output of 1 would ring around to the very first one and then put this back into a set condition, and there would be a 1. So essentially you're just moving the 1 around this register, ringing it, ringing it, ringing it, over and over and over. So this is what it looks like when you look at the waveform. You can see here it's just changing which Q output is on. That's it. But it's repeatable, okay? And so if you wanted to turn something on in a certain sequence, like this output turns on first, and this, whatever this is connected to, maybe this is a little digital buzzer or something like that, some component that you're turning on. Maybe it's a series of LEDs, right? You could do this in the lab, and that's what we would do in the lab, is we would assign these to LEDs, and then we would watch it ring around, right? It's kind of a neat one to watch. You could also do it with the 7-segment display, for that matter. You could take this Q output, put it through a 7447, and then drive the 7-segment display. So you can actually ring, if you had 7 of these flip-flops in a row, you could actually ring a 1 around the 7-segment display. It would go A, B, C, D, E, F, G, A, B, C, D, E, F, G, and it would rotate around. And so I've had students with extra time on their hands who would actually program like a little light show with a ring counter. So kind of neat things that you can do with it, but it allows you to do things in a sequence, because after Q0 is activated, the next one to activate is Q1, and you know that the next one to activate is Q2. So you can see here, it is kind of like a synchronous counter, except it's not producing a true binary output, but it's still producing a defined count. So you could look at this like it has a modulus to some degree, okay? It's not exactly the same as the modulus of a ripple counter, but it's still repeatable. You know how long it takes, how many clock cycles it takes to repeat, however many bits there are. So I would still, you could say that the modulus of this is 4, right? Because it counts, 0001 and then 0010, 0100, and then 1000, right? And it does that over and over and over. So the modulus is 4. There's 4 separate counts, okay? But this one, if we were going to design it like with ripple counters, we couldn't do it, right? Because you have to count in binary when you use those designs. Now the Johnson shift counter, also called a twisted ring counter, which I think is more accurate just because of the setup here. If you take a ring counter, and instead of taking the very last Q and feeding it back to the very top J, you cross it. Right? You have this cross connection that comes back down to the K. All right? So what you get is, you still get a repeatable signal, kind of like the ring shift counter, but this is the difference. This actually looks like a DC, a square wave, okay? Where it's on for a certain amount of time, it's off for the same amount of time. It's on for a certain amount of time, it's off for the same amount of time. So this is like a 50% duty cycle square wave, okay? And you can add more JK flip-flops if you would like to get a longer on time and a longer off time. But that's all you're doing. You're just taking the standard ring counter design and then shifting, or not shifting it, but crossing the very last two Qs here to feed back into the opposite J and K. All right? That's the only difference. You still have the automatic power reset here, and you're still only setting the very first, well, see, in this case we have the reset, 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 okay? So here's where you generate the 1 in a ring counter, so that is another difference. Obviously, the output of this very last one, if you have 0, 0 on the input, okay, you're going to get, if you have, let's see, this one would be reset, yeah. So all of the Qs are going to be 0, okay, which means all of the Q naughts are going to be 1. So, initially it starts out at 0, 0, 0, 0, but this Q naught is going to feed back into this J and put the very first one into a set condition, which is going to introduce a 1. That 1, 0 is going to push through, and then this Q0 will have made it through this one and now be pushed around. So you're going to have 4 bits of low, and then you're going to have 4 bits of high, and then 4 bits of low, etc., etc. So here you go, right? The Q, right? You can see it. So 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. And then we repeat back to the beginning, 0, 0, 0, 1. Okay? So if you looked at any one of these Qs, individually they could be used as a, like in this case, this could be used as a square wave signal to drive something else. Okay? So there's a lot of options here, and these are all shifted out one clock pulse. If you wanted to make them closer together, you could change the clock input. So you have a lot of flexibility here in what you can do. And again, there's an IC for that. Now, I'm not going to get as deep into the individual IC numbers here. Kleitz does a fine enough job of doing that on his own. But here we have a 74164, which is, to me, probably the most common. Okay, it's an 8-bit, which that's a lot. It's got 8 flip-flops in there. But think about how bytes are transmitted, right? A byte is 8 bits of information. So an 8-bit shift register is a very, very common shift register in digital electronics because you can send a byte at a time. In this case, we have a serial in, parallel out, and so it'll clock in 8 bits, and then it will release them in the parallel load out. So you can see here, it's just a bunch of D flip-flops internal. Okay. Here's a 74165. Now this one is a 7-bit serial or parallel load in and a serial out. And the way that you decide if you're going to parallel load in or not is this one bit here, okay, this one pin. And it's an active low pin, and so if you want to parallel load, you have to put in a 0, okay, because it's active low. Otherwise, if you have it tied high, then it's going to be a serial load in, I believe. It's either that or it's the other way around, okay? But anyway, it's an active low, parallel load, so that, yeah, it has to be. So when the parallel load input goes low, that's when you load in the parallel input. Okay, but it's a serial out, so you don't have any option to do a parallel out in this case. All right, so this one is more versatile because you have the option of how you want to load in your data. And a 74194. Now this one it goes all ways, right? Bidirectional, universal shift register. You can do parallel in, you can do serial in, you can do parallel out or serial out, and this 4 selector switch control mechanism, the S0 and the S1. I think the next slide shows you what those are. Yes. So here's the different operating modes of the 74194. If you just wanted to cover all your bases, then you could just use one of these. Hold condition is or hold, so whatever it's currently doing, I want to keep it that way. You can also change it in the middle of its operation. If you want to do a shift left, you put a 1, 0 on it. So if you want to do a shift right, you do a 0, 1 on the inputs. And then if you wanted to parallel load, you would do a 1, 1. Okay? And says 74-194 can be made by recirculating Q3 to D sub SR. Okay, and that's the D shift right. So again, when you go to look at the spec sheets for these IC chips, there's more going on than just what you see with the pinouts. Okay, and so sometimes they do more things than you even need it to do. But here's the complete select function table. Okay. And another timing waveform, same thing. You can follow the data here and watch how it shifts right or shifts left based on the mode that the IC chip is in. All right. Other thing I want to cover is called a tri-state output, or Kleitz likes to call it the three-state output. In other words, you can have a high, a low, or a float. In other words, you're in a high impedance state. And if you've ever thought about this, if you had multiple inputs that were going to share, multiple gate outputs that were going to share the same line, then you want to be able to sort of remove any influence from the unused outputs on there, okay? And so we use these tri-state outputs if they're all going to share the same line, right? So let's see, there's a 7435. So in other words, if I ask you this on a quiz or exam, essentially this is what I want you to get out of it. Connect the output of more than one register to the same points, and essentially one of them is going to be controlling that at that time. Okay, so if it's not actively producing a low or high output, it can be kind of in a stasis where it's in this high impedance mode where it's not distorting anything on the output line. Okay, and this is what it looks like. And then you essentially have this says output enable, right? Active low output enable. So when this thing gets a low on it, then it's going to let the input transfer to the output. Okay, but when it's not in use, when this thing is still high, then the output doesn't change. Okay, it's in a float condition, so it doesn't distort anything on the line. And let's see here. Ooh, traffic light controller. This is one of the things I do in my PLC class, is to create a traffic light controller using ladder logic, but you can also do the same thing with a few components in digital as well. All right, like I said, you can do almost everything with PLCs that you can do with, or vice versa. You can do everything in digital that you can do it with PLCs for the most part. So you can see here, if you had these components, you could actually create this. And what I don't like about this one is, it's not giving you any time. If you look at Kleitz's explanation of this, it's not giving you any time to clear the people who like to take off right when the light changes from red to green, and it also doesn't take into account the people who like to floor it through the intersection when they see a yellow light. Okay, so when one of those people is at the same intersection with the eager beaver in the other direction, that's where you can get accidents. And the way that this is set up here, it doesn't allow for both directions to be red at the same time, I don't believe. Okay, because I've seen similar ones to this before, but anyway, it still is going to rotate the green, yellow, red. Okay, just for a stoplight. But anyway, the really cool thing about this particular design is that I believe, it doesn't have the description here. It's got the description in the book. Whether it's day or night is whether or not the yellow is going to blink. Okay, and so it says low during the day, 1 pulse per second at night. So this yellow light is going to blink. So there must be it says a photo transistor or a photocell. It's going to operate until there's no light. When there's no light, that part of the circuit drops out, and essentially what you have here is this 1 pulse per second clock oscillator is going to blink this yellow light. Okay, so kind of a cool operation there. And you can see, this thing can easily be driven with a ring counter, right? Because that's all you need. You just need the outputs to turn on in a certain sequence. Okay, green, yellow, red, right? Okay. And let's see here. I think that's all I want to discuss. If you want to go further, and I'm gonna do the buffers here in a second too. I would encourage you to read through the stepper motor description that he has on there. We don't do anything like this in class, but if you wanted to know how a stepper motor works and how you could use a register to in this case you'd need one. Gosh, what is that? I guess you need 4 bits for this one, right? Is that what it's saying? Yeah, 4 bits for this one. So you can read about how they operate. It's a really great way to describe how the shift register works. And I wouldn't even look at the slides here. I would actually go to the book, and I'm not sure what page it's on. I've got the book open here. The traffic light. If you're playing along, the traffic light design is on page 647. And the stepper motor discussion is actually its own section of the book, 651, in chapter 13. Okay, and that's in the Kleitz book if you've got yours handy next to you. Okay, so the last thing I want to cover here is the 3-state buffer. So again, there's an IC for that, right? So it says used when output devices must share the same data bus. That's essentially a tri-state output, right? And so you can have now, what is this, 8 bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's 8. This is for the buffers. Yeah, I think there's what does this go up to? Oh, 3 on each side. So there's 4. Okay. But anyway, this allows all of them to be connected to the same line and provide isolation from each other, because you don't want one of the outputs to accidentally talk over, so to speak, another output that's supposed to be active. Okay, so I'll ask you about the 3-state buffer and also the tri-state output in general. Okay, I'm not going to make you remember that this is a 74LS244. Okay, but that is one of them. And definitely want to talk about this. The transceivers. So in any kind of communication, it's usually a few different ways. You have, if you think about radio transmission, that only goes in one direction, okay? The radio facility, the TV company, they output a signal from their satellite towers or wherever they're sending it from, all right? And so it's one-way communication, okay? So they send it out, you put an antenna in the air, and you grab the signal, and then it converts it into something that you can listen to or watch, right? Or both, okay? The other type is where you have 2 people on each end of the communication line, and both of them can talk to each other. It doesn't just go in one direction, okay? But think about, in terms of like the Nextel phones or just a generic walkie-talkie. How do those operate? Can you talk to each other at the same time? No. You are connected to the other person, but only one person can control the communication path at one time. Okay? And so whoever has control of it, that's the direction the communication is going from one end to the other. A bidirectional or a transceiver allows everything to happen at the same time. This is what happens when you have a conversation with somebody on a phone, right? You can both talk over each other at the same time, and the signals will make their way to the other end of the device, okay? So a transceiver is something that does both. It will receive transmissions, and it will also output transmissions, okay? I think that's all I want to cover here. So just to recap, shift registers used for serial to parallel to serial conversions. But somewhere lost in that is the fact that the whole purpose of this is that we're trying to get data from one place to another in an orderly fashion. And so when we can load it into a register and either hold it there until we need to move it, or we could go ahead and just load it in and immediately start moving it, depending on how we have our system set up. It says one common form of digital communication is for sending a computer to convert for a sending computer to convert its data from parallel to serial and then transmit over a telephone line and then to a receiving computer, which takes that serial data and then converts it to parallel form, and then it just parallel loads it right into the processor, right into the system. Okay. And it says simple shift registers can be constructed using the Q outputs of a JK flip-flop. And it says several flip-flops can be cascaded together this way, driven by a common clock to form multi-bit shift registers. And then there's two very specific forms of that, the ring counter and the Johnson shift counter. And that way we can create sequential control waveforms, which essentially we call those digital sequencers. And there's ICs that can do a few things. The 194 is the universal 4-bit shift register. It can go in either direction. It can receive and convert in either format. You just have to have the right mode enabled. All right, and then 3-state outputs, tri-state outputs have a high, low, and a float capability. And then the 3-state buffer is the one that where you can have multiples of those together into an IC chip. Okay. So you can see here it says latches transceivers are an integral part of microprocessor interface circuitry. They allow the microprocessor system to have external control of 8-bit groups of data, bytes. Buffer can be used to allow multiple input devices to feed a common point or to provide a high output current to a connected load. So they're all connected to the same output, which is counter to everything you learned in 112, right? And Quartus will throw a fit. But if you have 3-state outputs, then you can do it. No problem. Okay, I think I'll conclude my session.